subsets of a prime factorization. This video is created to supplement lesson 5.3, problem solving with combinations, because we can use subsets of prime factorization to count the total number of factors for a given number. We're going to learn some definitions that will be helpful. The sum is the result of addition, but the individual numbers used to add are referred to as addends. And the product is the result of multiplication. The individual numbers used to multiply are called factors. Prime numbers have exactly two factors. So some of these numbers include 2, 3, and 5 because the only way to multiply to get them is 1 times the number itself. So the opposite is composite numbers, numbers that have more than two factors. So for example, 4 could be multiplied as 1 times 4 or 2 times 2. So there's a total of 3 unique factors for the number 4. 6 is 1 times 6 or 2 times 3, and this has 4 different factors. And 8 has 4 factors as well. So these are referred to as composite numbers. And 1 is neither prime nor composite given these two definitions. It's not exactly 2 factors, because 1 times 1 is the only way to get it, and it doesn't have more than 2 factors. So one interesting result is that each number can be expressed as a unique product of prime factors. So here's a list of the first 10 numbers. And notice that on the right-hand side of the equal sign, we have a unique way of representing that number using only prime numbers. If you had a composite number, you would then be able to write it as a product involving prime numbers, and there is only one way to express each and every single number. So mathematicians often think of prime numbers as the fundamental building blocks of numbers. So what we're going to do is investigate the factors of a number. 300. So before we get into looking at this method that we can use involving subsets, let's understand why that is the case. So what I've done is created the following image. If we were to look at this factor tree, and what we can do for any number is write a product that creates that number, and once we've written out the factors, if it's prime, we're just going to give it a special notation. I've highlighted it red, you could circle it, but that's a prime number. 150 is composite because I can multiply it as 2 times 75. And if we continue in this manner, we'll end up with a prime factor at the bottom of the tree. And if we multiply each of those prime factors together, we get the prime factorization for a number. So each of these different selections of some of the prime factors will give you a set, and those numbers can be multiplied, and though the result of that multiplication, the product, will be a factor of the original number. So if we take 0 of the 2's, 0 of the 3's, and 0 of the 5's, we have not selected any of the prime factors. So we can think of this as we didn't select anything, the empty set. And we can replace that with the number 1 because it's not included, but we can think of this as multiplied by 1. So that null case or empty set can be thought of as 1 as a factor of 300. But for all other selections, let's just take one route randomly. We select 1, 2, and 2 5's. So that's the set illustrating what's been selected. But multiplying them together, 2 times 5 times 5 gives us 50. And that's an even number. So we're going to investigate how to find the total number of factors and the total number of even and odd factors. Let's start off with the total number of factors. Each of these different branches leads to an outcome that's one of the subsets of those selections. And in total, we can think of this as how many of the 2's are we going to select? Our options are either selecting none, 1, or 2. So using fundamental counting principle, we can think of this as a tree diagram or as a sequence of compound events. And let's try to get that all in the window. Same thing for 3. The number of choices that you have is either selecting 0 or 1. And for the numbers 5, you could have 0, 1, or 2. So looking at these outcomes, you might notice that each of these subsets represents one of the factors. All of these numbers divides 300, and it accounts for the total number of factors of 300. So the total number of factors of 300 is 3 times 2 times 3. Because remember, we can select 0, 1, or 2 of these. 0 or 1, that's 2 choices. Or for the 5s, 0, 1, or 2 5s. That product, using the fundamental counting principle, accounts for the total number of subsets. Now, an interesting investigation is that if you look at the results, the factors which are odd happen whenever no 2s are selected. That's the only section. This branch, everything from when we select 0 2s, results in an odd factor. So that will be helpful in counting the total number of odd factors. What we're going to do is force that selection. We're going to select 0 of the 2s, so that's one way that can happen. So we would do 1 times, and then it doesn't matter how many 3s and 5s we select because the product of 2 odd numbers is itself odd. So there is one way to select the number of 2s. We're going to select 0 of them to count the number of odd. But then we have 2 choices and then 3 choices. So notice that results in a total of 6, which is the number of odd factors that you see listed on the right-hand side. We could use the principle of the indirect method in order to account for the remaining outcomes, or you could think of the total number of even selections as requiring 1 or 2. As long as you have any 2s in your selection, that product will be even because the definition of even is divisible by 2. So a quick and easy way to calculate or count for these specific outcomes, the total number of factors, the numbers that are odd and the number that are even are here. And remember that the total number of factors is the number of ways that you can make subsets out of the prime factorization. The number of odd factors requires exactly 0 of the 2s to be selected because that's the only even prime number. And then how many of these factors are even? No 2 is selected. I believe that is wrong. If none are selected, then it's odd. That should say 2 is not selected. No, it does say that. And this should say at least 2 is selected. And that's why that can happen 2 ways, because you could select 1 or 2. All right. So here are some practice questions. Just try the numbers 680 and 14,000. Take a moment to pause the video and I'll show you the solutions momentarily. And you can use this as reference. Good luck.